Hey, how's it going? My name is Joseph Ryan Bernicki with Dr. Osbey's Aero Experiments class. And today we're going to be doing two different simulations. We're going to be doing one where we simulate NACA 2415 airfoil at a variety of different angle of attacks. And we're going to get velocity contours, pressure contours, and we're also going to get the coefficient of lift and coefficient of drag at those different angle of attacks. We're also going to be simulating a flat plate. We're going to get a couple important contours out of it in regards to velocity. And we're going to go ahead and get the skin friction coefficient. We're going to plot out things such as the Reynolds number. And a lot of this is going to be done through X and Y plots, but I'll show you that when we get to that point. So let's go ahead and let's look at our geometry first off for the airfoil. So let's just pull this up here in ANSYS. Perfect. So in this, I went ahead and I just did a real simple geometry, just large enough so that I would have no boundary layer effects from the walls. I did a circular inlet, and then I did just a flat outlet for the pressure. So I went ahead and I imported the curve, and then I had it shaped down to a surface so that I could go ahead and mesh everything out. So I probably should have just went ahead and opened up the mesh. Let's just close this and just go directly into the mesh. Now, the mesh for the airfoil was a little more difficult than meshes before because I found that to get accurate values, I really had to make sure that the skewness was low enough. And through this new handy tool of refinement, or not this actually, right here, yeah, you can see I just did the all triangles method. Let's go ahead and pull up the mesh so you can see it. Did the all triangles method. I did an edge sizing, so I made the number of divisions around the curve of the airfoil to 300, and then I went ahead and I did refinement of number 2 on the entire face, and that got my skewness down to 0.58519, which ended up being just fine. You'll see as I go through the results and everything that it's pretty close to what was expected and what I found from actual results from the NACA 2415. So as you can see, our mesh is pretty fine to make sure that we can get all of the important information around the boundary layer. So let's go ahead and exit out of this, and let's go into the simulation to show how we set it up. Hopefully it doesn't make me run the simulation again. Actually, I'm going to cancel this. I'm just going to go directly into solution. That way it doesn't make me rerun everything, because it is a lengthy process, and hopefully everything loads up pretty nice here. Okay. Has a number of iterations I was running, so hopefully it saved everything else. Graphics, yeah, cool. So we got everything. So let's go ahead into velocity here. Display this. And you can see this, what angle. So the way that I varied the angle of attacks was I went into the boundary conditions here, and you can see if I go into the inlet, edit, and then it'll allow me to put in the component. So this is actually at a 0 degree angle of attack. To change the angle of attack, I could go ahead and do the components of each one. So like, let's say I wanted to do the angle of attack of 10 degrees angle of attack. Then I could go ahead and put in 14.7721 into this X value, and then I can just take the sine of that angle as well. .604. So if I went ahead and put in those values into the X and Y, that would go ahead and give me a 10 degree angle of attack for the flow. So instead of actually changing the geometry, I just changed the flow's angle. It's going to give you the same results. It's just way easier than going in and changing your geometry each time you want to get the information. You can also do this through setting parameters, and you can have this all done in the workbench area of ANSYS. I tried playing with that, didn't get lucky with it, so I went ahead and did it this way. Let's go ahead and close out of this. I'm not trying to rerun a simulation. And let's go into our drag, compute, and then that's how we got our drag. We actually set up force reports in here. You can set it up for the lift coefficient, drag coefficient, and you want to make sure that you're doing it over the entire surface of the wing or the airfoil. And yeah, that'll give you both those values. And then once you have it set up, you can just go in here and hit compute. And then you can go in, change your angle of attack, and then all of your same settings are going to stay the same. Or all of your reports are going to stay the same, except it'll now do it at your different angle of attack. So let's go ahead. We have the velocity. Let's go ahead and look at the pressure. And there you can see a stagnation point. As we shifted the angle of attacks, you can see the stagnation point shifts with the angle of attack as well. So what else? We got the lift, we got the drag, we got the contours. We showed how we can vary angle of attacks. Okay, so I suppose let's go ahead and move on to the... Oh, another thing that I did differently in this simulation as opposed to the other ones, I actually had to adjust the turbulent viscosity ratio. I was using this one right here. I don't want to pronounce it because I'll make a fool of myself. And so this one right here, and I used it with a turbulence ratio of 1 instead of 10, which is the default value. And I found that my results were much more accurate with that. So, okay, perfect. So I believe that is basically everything. So let's go ahead and exit out of this. And then we can go ahead and hop into the flat plate simulation, how we did that. I actually kept the same mesh and everything. All I did was I removed the wing surface, or I removed the airfoil surface that was created in the previous one, and I just stuck in the rectangle at the dimensions that were required of us. So I did that. I ran basically the exact same calculation. Let me go ahead and pop in here. I actually didn't mean to open up the mesh. I meant to open up setup. Okay, well, let's go ahead and exit this because we do not need this. And let's go into setup. So hopefully last time I popped into the setup, it made me redo everything. It's probably gonna make me redo everything again, but we'll see. Or rerun the simulation at least. Yeah, so it doesn't have anything, but it already has everything programmed in here. I'm pretty sure it does. Okay, perfect. So yeah, let's go ahead. Let's just make sure we're at 10 meters per second. All right. Reference values, very important for these kinds of calculations. Calculated from the velocity inlet. We're going to go into the initialization, standard initialization, velocity inlet, initialize it, run the calculations. And I'm not going to run it all the way through because it takes forever to actually converge. But you'll see that our coefficient of drag here. Yeah, and it's giving me just about the same result as when I ran it last time. Lift coefficient should be near 0, which it looks like it's working its way to that. Perfect. Okay, so this is going to be the same exact thing that happened before. Once, I'm just going to wait for this to get a couple iterations through to make sure that everything's pretty accurate, but I'm not going to wait for it to converge. Because I know I've ran this before and it took a lot of iterations, which it shouldn't. I don't fully understand why it took a lot of iterations. The values I'm getting compared to the theoretical calculations I did are pretty good. They're not spot on as you would expect from doing a simulation as opposed to theoretical calculations, but it's close enough to where I felt it was acceptable. So I'm just gonna go ahead and stop it here. because again, I don't need to run through everything again. It's going through all the plots and everything that I need to generate. Now, let's go ahead and just look at the contours. So graphics, contours, velocity, display. So we can see here the boundary layer. And then this is, I went ahead and zoomed in when I did the zoom in for the report. I did the zoom in around the midpoint, but you can see the entire, how the flow reacts around the entire plate here with a stagnation point right up front. And then also we got the pressure contour, which wasn't asked for, but I just had it up there anyways. XY plots. So we went through, and this was one of my larger struggles throughout this, was actually getting the orientation of the XY plots to show the information that was necessary. The skin friction, the same thing. There was so much information that got pumped out of this. When I brought it into Excel, it was very hard lining everything up. And also my positions didn't exactly match, which I went through and I did some math, and this is very close to the length of my plate. But yeah, I mean, I still got the information I needed, and once I worked everything out, again, like I said, it was pretty close to the theoretical values. Like again, the velocity magnitude in this is reversed, but the position and everything makes sense. As I worked, as you get closer to the surface of the plate, the velocity due to the no slip condition is going to 0, but for some reason, it's just reversed. It's negative. So, and again, this has to do with the way that, from what I've researched over the hours of trying to figure out how to do this, the way that ANSYS calculates these values and the way that you have your vectors oriented can affect how the information comes across. So basically, I'm getting the right information. However, it's the wrong the wrong orientation. So I had to do a bunch of reorienting to make sure that everything was right. But I believe that's everything. This again is changed. This was not used in the report. But other than that, I believe that's going to cover, and the vectors. I forgot. The vector. So when I first did the vector plot as well, the heads on the arrows basically blended everything together. I tried to reduce the amount of arrows that were there, and it really didn't help that much. So I just did headless arrows, and it definitely, I mean, it still gets the point across. It displays what's happening, and it also displays the boundary layer and the no slip condition, which was the main focus of this anyways. So, and then that's pretty sweet, the recirculation. But nonetheless. Well, great. Well, I believe that's everything that needed to be covered. I appreciate your time. Thank you very much again. Have a great rest of your day.